Good evening to all. This is in continuation of series of videos on a steam turbine. Today the video is related to velocity triangle of impulse turbine. In this video you'll see how the velocity triangle is drawn in a stepwise manner, and you will also see the velocity construction of velocity triangle for real life examples. So I do hope you will like this video, and since this video is going to be very interesting, so please do keep watching until the end. Subscribe the channel and also share it. Please don't forget to hit the bell icon. If you want to see the videos of steam turbine of earlier videos, then you can visit to my you know description box where you see the links of these videos. So let's begin the videos of how velocity triangle is constructed. So first of all, let us understand velocity triangle in a real life example. First of all, what is relative velocity and absolute velocity? So if there is no motion of object, so there is no relative velocity. And if there is a motion, certainly you will see the relative motion or relative velocity. So thumb rule is that motion of object is no, that means there is no motion of object. Relative velocity is not possible. And if motion of object is yes, means there is a motion of the object, then you will see the relative velocity. So for to have relative velocity, the motion of object is a must. Take the case of on a small river where water is in a standstill. There is no flow of water, and if a swimmer wants to cross from this bank to this another side of bank in this direction, so the swimmer can cross with certain velocity, and this velocity is called absolute velocity. Since there is no flow or motion of water, so there will be no motion on the swimmer's body, and that is why whatever is the velocity of swimmer is the absolute velocity, and it has no deviation or no relative velocity. So if a swimmer starts from this point, it reaches to this point without any deviation, and this velocity is called the absolute velocity. So here there is no relative velocity because there is no flow of water. That means there is no motion of the body of swimmer, and so only absolute velocity. Now take the case of river which is flowing now. So since there is a velocity of the water or river, so certainly now swimmer wants to swim from one bank to another in this direction, that is perpendicular direction. Since there is a velocity of water which is flowing like this, so there will be velocity of the swimmer in this direction also. Since there is no motion in this direction, so there will be relative velocity and there will be absolute velocity. If you see, if a swimmer has a velocity from perpendicular direction from one end to another end, is relative velocity is this, and this is the velocity of river. That means this is the velocity of swimmer of body. So this will be absolute velocity because this, the vectorial summation of this plus this will become this. So in vector term, you can call absolute velocity is equal to relative velocity plus river velocity in this particular case. If you see the, in a small incremental, what is happening in fact, if a swimmer moves a certain distance, this, it will be carried away by the water and reaches this point. Similarly, next time it moves here, again water carries away to this point. Same way it moves further in this direction, water brings him back to this point, and finally it reaches to this point and water carries to this point. So you see, this is the movement or velocity of body, actual velocity. If observer from standing here, he can see the swimmer is moving like this, but for swimmer he can see is moving like this. As an observer outside, this bank can see the swimmer is moving like this. So this is absolute velocity, this is a relative velocity, and this is a velocity of river or water, which is equal to bodies or swimmer bodies velocity, which is acting on body in perpendicular direction. Now take the case of a train. Let's train is in a stop condition, which is in a station. So there is no motion of the train. So train velocity is 0 now. A stone is thrown here at an angle towards the train. So let's say this is a theta, which is thrown here. The velocity of the stone is called absolute velocity. And since train, there is no movement of train, so it is called absolute velocity. And person can see that, or passenger can see that it is striking at this angle. If you see this angle, so this is called only absolute velocity. There is no relative velocity because there is no motion of train. Now take the case of this one. Now train has velocity. Now this train, let's assume the train is moving with certain velocity, which is train velocity. So this is the train velocity. Now same way the stone is thrown the same angle, but since train is moving, it will strike here at this angle. You see, if you look at closely what is happening here, in fact, this is movement of a stone at certain distance. Since train has moved this direction, so this is relative velocity. Same way, a stone moves further this direction. Train moves from this point to this point, so this is relative velocity. Lastly, the stone moves this point and train moves this point, so relative velocity this. If you look at carefully, this point, this is the train velocity, and this plus this is the relative velocity, which is equal to this, and this is equal to this, and this plus this is called absolute velocity. So you will see that the same phenomena occurs. This stone is considered as a steam inlet, and movement of train is considered as a moving blade. You can later see how the velocity triangle is formed, and this is the angle at which a steam is striking the moving blade, and that is called the inlet blade angle of moving blade. You will see later. So same way you can think of this is the stone, it is striking to the train at this angle, not this angle. Earlier when train was in a stop condition, it was striking with this angle, but since train is moving, it will strike like this. A passenger on the train can see this relative velocity. The passenger can see that a stone is coming like this. So this is called relative velocity, this is absolute velocity, and this is a train velocity. Now, let's see condition of when train is in a stop condition. A passenger can alight or passenger can come out. Let's say in this direction. This is the velocity at which passenger coming out is called absolute velocity. Since train is in a stop condition, So whatever is the velocity of passenger is the absolute velocity. Since there is no movement of train, so no relative velocity. This is another example. If a passenger tries to move like this, if train is a stop condition and passenger is coming out in this direction with certain velocity, which is called again absolute velocity. Again, there is no relative velocity because train is in a stop condition. Now take the case when train is moving with certain velocity, and case a passenger is coming with this velocity. Now passenger is coming out in this direction, which is a relative velocity, and because of movement of train or motion of the train, the same motion will also apply on the body of passenger, and this passenger is carried away, and this is absolute velocity. You see, and that is why a person can fall if doesn't follow, that is why if person comes out while the moving train, he carried away in the direction of train. That is why a person, let's say, is coming out this because of movement of train. So his body is also moving in this direction. So he is carried away. It is comes here. So person which is observing from outside on platform can see a passenger is coming like this. Although the person who is coming out see he is moving like this. So this is called relative velocity. This is a movement of train. In fact, this is equal to this is movement of body of the passenger, and this is the absolute velocity. So now same thing you can apply. The train is a moving blade, and the person which is coming out, you can consider a steam coming out from the moving blade. The velocity at which a steam coming out from the moving blade is called relative velocity. And since moving blade is moving in this direction, that means the steam is also carried away in this direction. So this is absolute velocity of a steam. Same way you can think of, since let's say movement of steam here, then it's carried away here. So this is absolute. Further, it moves here and then carries away this way, and this is a flow. So if you add this plus this becomes the steam velocity, or sorry, train velocity or wheel velocity. And if you add this plus this is become relative velocity, and this plus this is called what is called absolute velocity. So this is the case when steam is coming out from the moving blade. Now these are the velocity terms. This is the inlet condition. This is outlet condition. Most important is that since the flow is in axial direction, that is axial inlet and axial outlet, that means we need to take the mean position or average position of the blade, and that is why all the terminology used in is as a mean condition or mean position. So inlet mean and outlet means are to be defined. Or velocity triangle is generated at the mean position of moving blade. So rotor, moving blade rotor, let us focus on moving blade. So moving blade, cross section area is the same at inlet and outlet of impulse turbine. You can see here the circle shows the inlet and outlet cross section area of the moving blade are same. This is a flow diagram of the moving steam is flowing in and out, and you will see since the area cross section area of the blade is the same, that means the relative velocity at inlet and outlet will same. This is the actual photograph of the blade, which is inlet and outlet are same. Now let's draw the inlet velocity triangle. So let's say draw a velocity c2. Just remember the train case. This is stone, that means this is steam, which is angle theta 2, sorry, theta 2 from the axial. This is axial axis of the rotor, and this is a rows of blades of moving blade. This is axis of rotor. So in the axis direction with an angle theta 2, which is a IGV, or which is a nozzle angle, it draw a C2, that is a inlet mean absolute velocity in the direction of moving blade. Now next step will be U2. It is nothing but train velocity. In this case, the moving blade velocity, tip velocity. Tip velocity is calculated pi d2n upon 60 into 1000. This is U2. So this is a inlet mean tip velocity. Tip velocity means done at mean position of the moving blade. Now inlet mean relative velocity. Now we have to join the starting point of C2 and a starting point of U2. So this is the V2. V2 is a inlet mean relative velocity. If you see, if you board on the wheel or board on the moving blade, you will see the steam is coming in this direction. That is inlet V2. That in V2 is the relative velocity. And you see this is the angle which is matching with V2. So this angle should equal to what is relative velocity, and this is how we design the blade angle based on this velocity triangle. Now inlet mean whirl velocity CW2 component and inlet mean axial velocity. Now C2 has two component. One is in the tangential direction, so CW2, which is equal to tangential component of inlet mean velocity, which is called inlet mean whirl velocity, and it has also axial component of C2 is called inlet mean axial velocity. And beta 2 you can see is a beta 2 is a blade angle. If you see, draw this line, this beta 2 and this beta 2 is the blade angle. So blade angle is this one. Now we need to draw the outlet velocity triangle. So outlet mean relative velocity V2, we have to draw V3, sorry, V3 with the outlet blade angle. So this is V3 which is drawn at beta 3, which is blade angle. Since this is impulse turbine, pure impulse, so there is no reaction. That means V3 is equal to V2, as cross section area this and this are same. Now outlet mean blade tip velocity, that is U3. Since it is measured at the mean blade, so both will be same at inlet and outlet. So U3 is equal to U2 because inlet mean diameter at inlet and outlet are same. That is D2 and D3 both are same. That is why U3 is equal to U2. So you have to draw U3 which is equal to U2. Now we have to join the starting point of V3 and end point of U3. This is absolute velocity at outlet. You see, you can think of, the passenger coming out and it is carried away by the motion of the train. This is the same thing. Steam is coming out and then it is carried away because of the motion of the moving blade, and that is why it reaches here. And so this is called C3. It has now two component, we'll see later. Outlet mean whirl velocity, so it has tangential component. This is a small one is a tangential component because it has tangential component is CW3, and axial component is a CA3. This is axial component of this is a CA3, and theta 3, this theta 3 is the outer absolute blade angle measured from the axial. So the steam is coming out with an absolute velocity, with an angle theta 3 beta 3, theta 3 from the axial for absolute velocity, that is C3. So I hope you have enjoyed the session for construction of velocity triangle for impulse turbine, and also correlation of the real life example. So thank you for watching.